Chapter 4 for the AP Chem review of reactions in aqueous solutions. First, begin off with properties of solution. A solution is referred to as a homogeneous mixture. It's composed of a solvent, which is the substance in large amounts that's doing the dissolving, typically water. And a solute is a substance in small amounts, which is the thing being dissolved. An electrolyte is a solution that can conduct electricity. Ionic compounds are very good at this because they have ions floating around in solution. For example, if I put sodium chloride in water, I'd have Na plus and Cl minus floating around. That would be able to conduct electricity. Hydration is the process in which an ion is surrounded by water molecules arranged in a specific manner. Now, we could give you a general example of acetic acid. What really happens with acetic acid is you end up with something like, first off, acetic acid is HC2H3O2. If you add that into water, what can happen is the acetate ion, the C2H3O2, is going to be surrounded by water molecules. The hydrogen actually is going to add on to the H2O and make an acid, which we'll talk about more later. By the way, when I draw an arrow that looks in both directions, that's referring to a reversible reaction. So that's a reaction can happen in both directions. So the products of C2H3O2 minus, and then the hydronium ion in this case, which is H3O plus. This would be an aqueous, these would be aqueous, that would be a liquid. Precipitation reactions, something we covered a lot in Chem 1. Precipitation is an insoluble solid that separates from the solution. If you recall, in Chem 1, we had you with the solubility table kind of do a look, and here, if it hits an I, that's insoluble, which makes it a solid. So that solubility table is something that you'd have to remember how to work. An example of double displacement would be the reaction between lead-2 nitrate and potassium iodide, which, by the way, again, metathesis is another term for double displacement. We always use double displacement. So lead-2 nitrate is PbNO3, 2. That's a solution, that's aqueous. Plus potassium iodide, 2Ki, I'm just balancing right away, is going to make potassium nitrate, KNO3. Sorry that I'm running out of room. My solid is the PbI2. The reason I know that PbI2, lead-2 iodide, is my solid is if I look on the solubility table, lead and iodine hit up an I. I meaning insoluble, so that has to be the one that does not dissolve in water. Everything else is aqueous. If I continue on with this, solubility refers to the maximum amount of solute that can dissolve at any specific temperature. Now, molecular equations, the PbI2 solid, we're going to give that as an example for what's referred to as an ionic and a net ionic equation. So a lot of students don't like doing this from Chem 1, but right here is the molecular equation. This is PbNO3 2 plus Ki, making KNO3 plus PbI2. So that one's already done. An ionic equation shows that since the lead-2 nitrate is aqueous, it has ions floating around in solution. So a more accurate way to represent lead-2 nitrate would be, I have a Pb plus 2 and 2 NO3 minuses floating around. So this means the exact same thing as this when it's aqueous. I also have 2 K plus ions and 2 I minus ions. All this is going to yield, and again, sorry that I'm running out of room, I'm just going to draw the rest down here, 2 K plus ions plus 2 NO3 ions plus the PbI2. Solids do not get broken up in an ionic equation because those are the things that are insoluble. They do not float around as ions in the solution, which is why this allows a double displacement reaction to occur, is by making this solid. So now I have all these ions to begin with. They create these ions and that solid, which leads us to the net ionic equation. There's two ways to look at the net ionic equation. One is to get rid of the spectator ions. A spectator ion is what starts and ends an equation. For example, the K plus is on both sides of the arrow. I'd get rid of it. The 2 NO3s are on both sides of the arrow. I'd get rid of it. And what I'd be left with is my ionic equation of what things actually reacted. The lead plus 2 and the 2 iodines are the things that reacted to make the PbI2 solid. So this right here would be the net ionic equation. Moving on, if we talk a little bit about acid-base reactions, first off on the board is a whole bunch of general properties of acid bases. Acids, for example, have a sour taste, they cause a color change in plants, they react with metals and carbonates, and they conduct electricity. Bases have a bitter taste. They're slippery to the touch. You'll see them in cleaning products an awful lot. They can also cause color change in plants. That's the whole indicator idea. And then they are also good at conducting electricity. There's several different definitions of what makes something an acid or a base. We're going to start off with the Arrhenius definition. The Arrhenius definition says an acid is anything that makes hydronium. A base is anything that makes hydroxide. An example, hydrochloric acid, HCl, when you put it in water, will make H3O plus Cl minus. Here's your hydronium. It made hydronium, therefore HCl must be an acid. If we did the base version, sodium hydroxide, which is an ionic compound, in the presence of water, will make Na plus and OH minus. There's our hydroxide. It must be a base for sodium hydroxide. The Bronsted-Lowry definition says that an acid is going to donate a proton. A base is going to accept. If you look at HCl, HCl gets rid of its H. The H goes over here. It's donating a proton. So by donating a proton, it makes the hydronium anyways. So there's two ways to look at why that's going to be an acid. And again, with the base, if you are accepting a hydroxide. Accepting that. A Lewis dot definition will also work for an acid. A Lewis definition is an electron pair acceptor or donor. For this one, I'm going to show you HCl as an example. But I have to draw out the Lewis dot to do it. Here's HCl. If I add it to water, the mechanism that occurs, HCl won't just give its hydrogen away. Instead, what happens is these two electrons on water grab the H. These two electrons in the bond will then get deposited around the chlorine. So our products of this reaction would be a Cl minus. And then the HOH, the hydronium plus. If you notice, the chlorine accepted electrons. It's actually the opposite for the Bronsted-Lowry. If you accept a proton, that means you donate electrons. If you donate a proton, you accept electrons. So the two are kind of inversely working with one another. Next thing to mention is an acid is basically anything that has a hydrogen on it and that can donate that hydrogen. There are things called monoprotic acids. An example could be HNO3, nitric acid. It has one hydrogen to give. A diprotic acid could be sulfurous acid. Why it's called diprotic is because it has two hydrogens to give. A triprotic could be phosphoric acid, H3PO4. Why is it called triprotic? It has three hydrogens to give. And I actually could show you how H3PO4 plus water makes H2PO4 minus plus hydronium. Then an H2PO4 plus water can make HPO4 minus 2 plus hydronium. We don't have time to go over all that, but again, when I showed you how something can donate a hydrogen, this can donate three hydrogens. Neutralization reactions are next. A neutralization reaction typically is what makes water and a salt. An example could be HCl plus NaOH. A lot of students will think of this as a double displacement reaction because basically the hydrogen and the sodium are trading places. HOH is just water plus sodium chloride would be other products of that reaction. Some of these neutralization reactions will also make a gas. An example would be HCl plus CaCO3. Still can think of it as a double displacement of sorts. I'm going to put a 2 in front of here to balance that out right away. But we're not going to have H2CO3 as a product. Instead, we're going to have the H2O because it's neutralization. We're going to have the calcium and the chlorine, calcium chloride. And lastly, carbon dioxide gas will be created as well. When you see a carbonate within the formula of the base, it will make carbon dioxide as one of its products. Oxidation and reduction reactions are next. Often referred to as redox reactions. This is where electrons transfer, and a lot of reactions will have this. Oxidation is referred to as the loss of electrons. Reduction is referred to as the gaining of electrons. This is where, once again, we do Leo goes Ger. Lose electrons oxidized, gain electrons reduced. Now, two other terms you need to be familiar with is one, oxidizing agent, which is causing something to lose electrons, and then lastly, reducing agent, which is causing something to gain electrons. It's kind of weird. Your oxidizing agent is the thing that's being reduced. The reducing agent is the thing being oxidized. It's just very common to use the agent terms. Continue on with oxidation reduction. In a redox equation, you must have both the oxidation and the reduction reaction. Here are some rules for oxidation numbers. First off, if an element stands alone, it's given a 0 oxidation number. Hydrogen is usually a +1 unless it's going to be bonded to a metal. The charges of the metal usually are its oxidation number. The more electronegative nonmetal will have their charge as their oxidation number. And then a common one is the peroxide. The oxygen is -1. I'm going to give you a simple example of the synthesis of magnesium oxide, which is magnesium plus oxygen making magnesium oxide. And I can balance this equation if I want to. To assign oxidation numbers, magnesium stands alone. It's given a 0 oxidation number. The O2 stands alone. It's given a 0 oxidation number. Now, when you don't stand alone is when you're bonded to something else. So here, magnesium is bonded to oxygen. Magnesium's charge in here is a +2, same as its oxidation number. Oxygen's a -2. What you would need to do then is identify what is oxidized, what is reduced. Remember that electrons are negative. So if magnesium starts as a 0 and it goes to a +2, it lost electrons. Lose electrons, it's oxidized. So the magnesium was oxidized. The oxygen went from a 0 to a -2. It gained electrons, it's reduced. And we'll go over how to write half reactions later on, but that's something we have to remember of how to identify it. And not only that, if magnesium was oxidized, it makes it the reducing agent. If oxygen was reduced, it makes it the oxidizing agent. Last thing to say before we move on to the next slide is the old definition of oxidation was gaining an oxygen. You see, magnesium starts alone, it gained an oxygen. So right away you can know, hey, magnesium was oxidized. There are several different types of redox reactions that we can go over. First off is called combustion. Combustion is when you have a carbon-hydrogen compound reacting with oxygen to make carbon dioxide and water. An example could be the burning of hexane. So here's my carbon-hydrogen compound, my alkane plus oxygen, making carbon dioxide and water. I put a 19 in front of the oxygen, a 12 in front of the CO2, and a 14 in front of the water to make that balanced. So we've talked about combustion reactions a lot though. Second one is decomposition. Take for example sodium hydride. Sodium hydride is NaH. That will yield Na plus H2 because it is a diatomic. I put a 2 in front of that as well. And this is also an oxidation reduction because these are zeros, a +1 and a -1. Single displacement. There's 3 different kinds of single displacement. We don't have time to go over all of them, but hydrogen displacement is when a metal is added to water, so the metal takes the place of the hydrogen in water. A metal displacement, you look on your activity series. Something like magnesium plus silver nitrate would make magnesium nitrate and silver. And then lastly, a halogen displacement, like we did in the Chem1 halogen lab, could be something like sodium bromide plus fluorine, fluorine being an F2, would then give you sodium fluoride and bromine. All types of redox reactions, single displacement, decomposition, combustion, synthesis commonly is as well. Disproportionate reaction is the last one to bring up. That's the decomposition of hydrogen peroxide. Disproportionate reaction is very unusual. The same element is both oxidized and reduced. So I want to show you that example before we move on to the last couple of slides. H2O2 is hydrogen peroxide. it makes H2O, which is water, plus O2. If I assign oxidation numbers, hydrogen's a +1, oxygen in a peroxide is a -1. Hydrogen's a +1 here, this oxygen's a -2, that oxygen's a 0. Hydrogen, you notice, doesn't change at all. Oxygen goes from a -1 to a -2, which means it must have gained electrons, is reduced. Oxygen also went from a -1 to a 0, which means it lost electrons, it is oxidized. So it's unusual, but sometimes the same element can both be oxidized and reduced. The last 2 slides for this chapter deal with concentration of solutions. Molarity is the most common concentration that we use, that's moles of solute over liters of solution. And we'll give you an example of a problem. What is the molarity of an 85.0 milliliter ethanol solution containing 1.77 grams? So, molarity, we often say, again, is moles per liter. Sometimes we even give you this triangle to realize that you can solve for anything within that equation. Now, in this particular question, it asks for the molarity, so I'm going to take moles divided by liter. But if I want to solve for grams or moles, I'd cover up that and take molarity times liters as my first step. All right, here we go. If I start off with 1.77 grams of ethanol, which is C2H6O, I will then convert that into moles. 1 mole over, look at the mass from the periodic table, 46.08 grams. That would give me a number of moles of 0.0384. Divide that by my liters, 0.085 liters. 85 milliliters converted to liters. And that would give me a final answer of 0.452 molar ethanol. So that's the simplest way we give you molarity. A dilution is something else that we deal with concentrations. It's making something less concentrated. The equation that I typically used was M1V1 equals M2V2. Sometimes you might see it as C1V1 equals C2V2, which the C stands for concentration instead of molarity. Here's an example. How would you prepare a 200 milliliter solution of 0.866 molar NaOH from 5.07 molar? If I start with M1V1 equals M2V2, my initial molarity is a 5.07. That's the potent stuff, the stuff that I want to water down. I want to figure out what the volume of that's going to be, so that's multiplied times V1. The M2 is what concentration do I want to make? The 0.866 molar. What is the volume? 200 milliliters. You could convert this to liters if you want to, but it doesn't matter. V1 in this case is going to equal 34.2 milliliters, which means if I wanted to make a 200 milliliter solution, 34.2 milliliters would be the concentrated stuff. Add water to get it up to the appropriate volume. The very last thing is actually using the same equation, except for with titrations. A standard solution is added to an unknown concentration until the reaction is complete with an acid-base reaction or titration. The equivalency point is the point where the acid has completely reacted with the base. And the very last thing we're going to do is this practice problem. It says how many milliliters of 1.28 molar sulfuric acid are needed to neutralize 60.2 milliliters of 0.427 molar potassium hydroxide. First thing I do during a titration problem is write down the balanced equation. H2SO4 plus 2KOH makes K2SO4 plus H2O. The next thing I'll do, and I put a 2 in front there, is my M1V1 equals M2V2. But instead of this being initial and final, I'm going to treat this as acid must equal out the base. So the moles of acid should equal the moles of the base. So now I have 1.28 molar sulfuric acid, and I'm trying to solve for how many milliliters of that, so V1 equals my M2 is the 0.427 molar times the 60.2 milliliters. If I solve for V1 in this case, that gets me 20.1 milliliters. If this were a 1-to-1 ratio of acid to base, we'd be done with the problem. But it's not a 1-to-1 ratio, it's a 1-to-2 ratio. So really, if I do a conversion of H2SO4 over KOH, I need to divide this by 2. 10.1 milliliters is all I need of the acid because I need twice as much base to react with it in the first place. It's a diprotic acid. So again, what you want to do is M1V1 equals M2V2, 1-to-1 ratio, you'd be done. If it's not, then you might have to multiply or divide by 2, depending upon what you solve for in the first place. And that is the end of chapter